So let's now consider the case of diatomic nitrogen N2. How do we proceed to draw the Lewis structure? Well, we start off by putting down the two nitrogen atoms, and we put the valence electrons around them. Well, in which group is nitrogen? If you look at the periodic table, it's group 5. So each nitrogen atom will have 5 dots. It doesn't matter how you write down those dots. The best way to do it is to write, just distribute them around the atom in a reasonable way. Now we've got to try and match these things together to achieve noble gas configuration. How are we going to do that? Well, here's one strategy. We can bring those two together, and then we get something like this. That's no good, because if you count the electrons around it doesn't achieve noble gas configuration. So we shift more electrons around until we get to this point over here. So here we have, in fact, 6 shared electrons between the two nitrogen atoms. A triple bond, and each nitrogen atom has a lone pair. So it's really like playing a game where you put on and it's really a lot of fun, right? Once you can do it, it's great. It's very rewarding to write down the Lewis structure and count the electrons and see that everything works out. Okay, so that's basically, we've now looked at double bonds, single bonds. Try and get the octet rule, or the noble gas configuration for each atom by moving the electrons around as you need to. All right, now let's look at some other examples. Let's look at, for example, ammonia, NH3. Now, let's actually, in fact, do that one together on the board. Ammonia, NH3. So how do we proceed? Well, it seems reasonable to me that the nitrogen atom would be in the center. So let's put the nitrogen atom in the center, and let's just put the H's around it. Something like that. Now let's put in the valence electrons. Hydrogen has 1. Each hydrogen has 1. And how many does nitrogen have? 5. Let's just put them in. 1, 2, 3, 4, 5. Something like that. So what are we going to do? Well, we have an unpaired electron here, here, and here for the hydrogen. So those obviously are going to form a bond with the nitrogen and will require an electron from the nitrogen. So the way that I do it is I sort of draw circles around it, something like that, and we match those up. And if we do it in that way, what I really have is something like this. Does that have noble gas configuration? Yes. So there we go. That's the Lewis structure. You just need to practice it. And remember, you can move electrons around through as you want, basically. Okay. So that's just an example. What I have on the next slide here are some ball and stick models. We call these ball and stick models for a variety of molecules. Here we have ammonia. We're going to get to these shapes in a moment, right? But anyway, this is sort of the models of these molecules. That's formaldehyde, right? Water, carbon dioxide, we've already seen SO2, sulfur dioxide, and methane. Okay. Now, here again, just for your own information, if you want to, I in fact have really a step-by-step guide to help you how to write Lewis structures if you want it. I don't do it like that. I don't like doing it like that, but some people prefer having a step-by-step way of doing it. And also some general rules here on the left. Basically, what it really boils down to is that we want to get noble gas configuration. However we get there is sort of up to you. The next thing I want to discuss is the notion of formal charge, resonance, and exceptions to the octet rule. So there's, of course, in science always exceptions. And the first thing I want to discuss is formal charge. Now, formal charge is not something that we can actually measure, right, in a laboratory. We can measure the charge of something, but we can't measure the formal charge. Formal charge is sort of really something that we've dreamt up to take into consideration bond polarity, right? So the definition is the atoms in polar covalent bonds have partially positive or partially negative charges, however no full charge transfer takes place. Now, really what we've come up with as chemists is the notion of a formal charge, which is calculated by this formula. Okay, it's a formula that looks very complicated. It isn't complicated at all. But once you've drawn a Lewis structure, you can evaluate the formal charge of all the atoms in that Lewis structure very simply by considering each atom individually, looking at the number of valence electrons, in other words, which group is that atom in, subtract the number of lone pairs, minus half the number of bonding pairs, and that will give you the formal charge of that atom in the Lewis structure. It might be 0, it might be +1, it might be -1, +2, or -2, but if you sum all the formal charges of the individual atoms in a molecule, it must add up to the charge, the measurable charge of the thing, the ion or compound that you're studying. So let's look at some examples. Here I have a Lewis structure. In fact, this is not a very good Lewis structure, incidentally, of BF3. Okay? Now we're going to get to this in a moment because, in fact, this is an example of a compound that, in fact, deviates from the octet rule. It's an exception to the octet rule, BF3. Now let's consider this fluorine atom over here. What is its formal charge? How do we calculate it? Well, it's in group 7, it's a halogen. So 7 minus the number of lone pairs, we've got 6 lone pairs. So 7 minus 6 is 1, minus half the number of bonding pairs. How many bonding pairs do we have? How many bonding pair electrons do we have, I should say, sorry. 2. So half the number of bonding pair electrons, this line represents a bonding pair. So it is 7 minus 6 minus a half of 2, which is 1, which is how much? 0. So this atom has no formal charge. But let's look at this boron atom over here. Okay, well, I've already written the result there, -1. Boron is in group 3. That means it has 3 valence electrons. How many lone pairs does this boron atom have? None. How many bonding pair electrons does it have in total? 2, 4, 6, 8, because it's a double bond. So how many, what is half of 8? 4. So what is 3 minus 4? Minus 1. So the formal charge of boron is -1 in this Lewis structure, and the same for fluorine. All right, so that's an example of, well, that's how we calculate formal charge. And in the tutorial, there's many practice examples. This is very important. I don't want to discuss that. What I want to now discuss is the notion of resonance. All right. Now, the notion of resonance comes from the fact that sometimes I can write several acceptable Lewis structures for a molecule, an ion, whatever. And if I can write several acceptable Lewis structures for something, you can't, pick one and not the other. You have to pick all of them at the same time, because they're all acceptable Lewis structures. And that's what resonance is all about. So here, for example, let's consider the nitrate ion, NO3-. This is the Lewis structure. If I happen to write down the Lewis structure of NO3, I might end up with something that looks like this. It's perfectly reasonable. All the atoms have 8 electrons around them. They all obey the octet rule. Another person sitting next to me might draw the Lewis structure like this. In other words, with a double bond between this nitrogen and this oxygen atom. I have the double bond between this nitrogen and this oxygen atom. Another person might write it like this. But notice all 3 of these resonance structures are perfectly reasonable. They all fulfill the octet rule. They all have 8 electrons around them, and they're all perfectly okay. So I can't just pick one and not the other. I have to pick all 3. And in fact, that is what resonance is all about. Basically, picking all 3 of these, which depict the average of these 3 structures, sort of depict the real bonding situation of the nitrates ion in reality. That's the way to think about this. And generally we have, with resonance, we usually only have resonance structures usually when we have multiple bonds. So you see what I'm basically doing is I can move this double bond from here to here and from here to here. How do I do that? Well, I'll make that lone pair over there, just push it in there. That becomes then a bonding pair. And that bonding pair I can put onto that oxygen atom there and becomes a lone pair. So you move you're basically pushing electrons around. Something that, by the way, becomes very important in organic chemistry later on, the ability to push electrons around. That's what I'm doing here in resonance. Now the way to think about resonance structures, and this is very important because I think many students don't understand the notion of a resonance structure, is to think of orange paint. If I have orange paint and I paint it on a canvas, it's orange. But what is orange paint? Orange paint, I make orange paint from red paint and yellow paint, right? If I mix red and yellow, I get orange. But if I have orange paint on the canvas, it's just orange. It's not red the 1 minute, and then yellow, and then red again. It's the combination of those 2 colors. Resonance structures are the same. If you have a bottle of potassium nitrate, it's not like 1 second the molecule or the ion looks like this, and then it changes to this, and then here, and then back again. It is the combination of all 3 of those structures fused together. And that is what resonance is all about. Okay? And moreover, actually, what it tells us, if we fuse all of these together, that the nature of the nitrogen-oxygen bond in a nitrate ion is going to be somewhere between a single and a double bond. Do you see that? Because here in this resonance structure, I have a double bond between this nitrogen and this oxygen. Here it's a single bond, here it's a single bond. Same for this one, here it's a single, then a double, then a single again. Here I have for this nitrogen-oxygen bond, single, single, double. So if we fuse all of those together, basically the bonding nature of the nitrogen-oxygen bond will be somewhere between a single and a double bond. So remember that analogy of the orange paint, right? That's what resonance is all about. Here we have another example, SO2. Here we've got, in this resonance structure, the double bond between sulfur and oxygen. Here we have the double bond between this sulfur and this oxygen atom. They are both perfectly acceptable Lewis structures. So I use this double-headed arrow to indicate that there are 2 resonance structures for sulfur dioxide, and also what it tells us is that the bond order, in fact, is between a single and a double bond for each sulfur oxygen atom. And here we have the example of NO2 minus, the nitrite ion, same thing. Any questions? Yes?
What is bond order that you just mentioned?
Oh, the bond order, yes, it's a very good question. Well, essentially, in bond order is whether I'm talking about a single bond, you know, with 2 shared electrons, a double bond, 4 shared electrons, or a triple bond, 6 shared electrons. So if I'd say the bond order is 1, I mean it's a single bond. If the bond order is 2, I mean it's a double bond, and so on. So if the bond order is between, you can see here the bond order for each of these nitrogen-oxygen atoms is somewhere between a single and a double bond because of resonance. Everyone follow that? All right. If you don't, please ask questions. Okay, now, we have exceptions to the so-called octet rule. And the first exception is that we have radicals. Radicals are species with unpaired electrons. Here, for example, we have a CH3 radical, a methyl radical. No matter what you do, there is no way that you're going to get an octet of electrons around that. Same here with NO. If you write the Lewis structure of NO, there's an uneven number of electrons, and there's nothing that you can do about that. It exists as a species with an unpaired electron. Radicals, species with unpaired electrons, tend to be extremely reactive, right? They're not stable generally. There are some examples in the literature of compounds that are stable and crystalline but radical in nature, but generally they tend to be highly reactive. And here we have an OH radical. This is not OH minus hydroxide, this is an OH radical. If you write the Lewis structure of oxygen and hydrogen, no matter how you move the electrons around, you're going to end up in every Lewis structure with an uneven number of electrons. So these are exceptions to the octet rule. We have for group 3 elements, and also for some group 2 elements, beryllium, for example, and also as you saw in hydrogen, incomplete octets. And basically, if we take, for example, boron trifluoride, BF3, if we write the Lewis structure, no matter what we do, we're going to end up with an incomplete octet, right? I want you for the moment just to forget about these two Lewis structures here, or these resonance structures, because just forget about that. Focus your attention, please, on this one here. BF3, this is the Lewis structure. Boron has 3 valence electrons. Each fluorine atom has 7. And if I write the Lewis structure, I end up with the boron with only 6 valence electrons, right? Now what I could do to try and fulfill the octet rule is move one of these lone pairs to, like I've done in the second resonance structure here, to do something like this. But the problem with that is, okay, then the boron and the fluorine have 8 electrons around them. So, you know, we've complied with the octet rule, but then I introduce formal charges on the boron and the fluorine. Now there's sort of a hand-waving rule when you're drawing Lewis structures that you should try and minimize having formal charges as far as possible on the atoms, right? Because, of course, you know, we don't want formal charges. Formal charges on atoms make things, tend to make things unstable. So minimize atoms with formal charges. So this Lewis structure over here is in principle possible, but it introduces formal charges on the boron and the fluorine, which is not really very desirable. Same thing here. What I've done here is something more crazy. I've actually completely broken this bond here. So this is an example. Group 3 elements, aluminium, boron, and so on, tend to have an incomplete number of electrons in complete octets. Same with beryllium. So the third thing, and the most important thing, are expanded octets. Now, when I'm dealing with heavier elements, so elements in period 3 and above, period 3 being, let's go to the periodic table just so that we know where we're at. So these elements here, so this is period 1, period 2, this is period 3. So if I'm dealing with elements in period 3, on P block elements in period 3 and higher, so aluminium, silicon, phosphorus, sulfur, chlorine, and so on, these orbitals, if you look at the electron configuration, have d orbitals. D orbitals available to participate in bonding. And these d orbitals therefore enable an expansion of the octet. So we can have, in fact, more than 8 electrons around these atoms if they are the central atoms in a Lewis structure. Okay, so let's have a look at that. By the way, I should mention that what I'm telling you now, strictly speaking, is incorrect, right? Strictly speaking, if you're a chemist, what I'm saying now is totally wrong. But this is just a bonding model, right? It's a model that's actually not correct, but it's very useful in predicting the shapes of molecules. But we have more advanced and sophisticated theories that chemists use, which sort of approaches reality in a much better way. Just appreciate this is a model that we're using, a very outdated model, but a useful one nevertheless. So heavy p block elements, or elements that have access to d orbitals, can, in principle, have expanded octets. So let's take phosphorus trichloride as an example. If we draw the Lewis structure, we end up with something like this. Phosphorus is in group 5, So we have 1, 2, 3, 4, 5. Chlorines each have 7. And that's the Lewis structure we end up with. How many valence electrons do we have on the phosphorus atom? Well, we have, in this case, 2, 4, 6, 8. So that's okay. But what about phosphorus pentachloride? We play the same game and we end up with a Lewis structure that looks like that. And in this case, we've got 10 valence electrons around the phosphorus. That's totally okay, because phosphorus is a is in the third period, so it has access to d orbitals, so it can have an expanded octet. Same with sulfur hexafluoride. So sulfur is in group 6, it is in period 3, it has access to d orbitals, so it can undergo an expansion of the octet, and we end up with, in this case, 12 electrons. Now, I'm going to get to essentially the last topic today, which is, I again cannot stress the importance of this. This is of paramount importance. First of all, if you cannot draw a Lewis structure properly, you can't do this. So the one builds on the other. And I'm going to introduce the notion of VSEPR theory, which stands for valence shell electron pair repulsion theory. Now, this is a beautiful theory, a very nice theory, where if we start off with a Lewis structure, we can predict the shape of the molecule, which is great. Just think about it. You're confronted with a molecule, you write down a reasonable Lewis structure, you can actually predict what shape it's going to have. Now, how this theory basically works, I'm going to cut to the chase, is it relies on what's happening around the central atom. And in order to figure out what's happening around the central atom, we need, of course, the right Lewis structure. So, depending on what's happening around the central atom, we have, we can predict the geometry. So, this depends on the number of electron pairs around the central atom. So the geometry is not dictated by the peripheral atoms. Doesn't matter what's going on there. We're talking about the central atom. And we do have a task on this as well, so we're really going to get into this. Let's take methane, for example. If we draw the Lewis structure of methane, it basically has carbon with 4 hydrogen atoms around it. So it has 4 bonding pairs. It has 4 bonding pairs around the central atom. 1, 2, 3, 4. Ammonia, if we draw the Lewis structure of ammonia, we just did that a moment ago, we have 3 bonding pairs and 1 lone pair. Water, we also drew the Lewis structure of water a moment ago, has in fact 2 bonding pairs and 2 lone pairs. What is the similarity in these 3 structures? Can someone tell me what is the same and what is different? Anyone want to venture a guess? Well, what is the same is the total number of electron pairs around the carbon. Here I've got 4 bonding pairs. Here I've got 3 bonding pairs and 1 lone pair, but I've still got 4 electron pairs in total. 3 bonding and 1 lone pair. In water I have 2 bonding pairs and 2 lone pairs. 2 plus 2 is 4. So how this VSEPR works is we have a certain notation. X defines a bonding pair, A is the central atom, and E is a lone pair. So we have AX4, because we've got 4 bonding pairs, AX3E, because we've got 3 bonding pairs and 1 lone pair around A, which is the central atom, in this case carbon, and we here have for water H2O, 2 bonding pairs, 2 lone pairs. But notice it's the same number of what we call electron pairs, or same number of electron pairs. All of these have an electron pair or electron group geometry, which we call tetrahedral. That's the electron pair geometry. The molecular geometry depends on how many lone pairs we have in each of these structures. So here we've got, so the electron pair geometry around ammonia is tetrahedral. The electron pair geometry around in water is also tetrahedral, but the molecular geometry is going to change because I've replaced one of the bonding pairs with a lone pair. So of course that's going to affect the actual molecular shape. And that will be trigonal, bipyramidal, and in the case of water we call it bent. Everyone understand that? No. All right. Questions? Yes.
If you ask us for giving the molecular shape, then we have to write the number, like the notion, or
no. The molecular shape is tetrahedral, trigonal, pyramidal, or bent.
Okay, then we
But in order to get to that point, you need to get first the right Lewis structure. From the correct Lewis structure, you figure out what the electron group or electron pair geometry is. In other words, how many bonding pairs are around the central atom. That will tell you what the electron group geometry is. And then depending on how many lone pairs you have, you can figure out the molecular geometry. That's the process. Now I'm going to show you a table of this, which might make things a little bit clearer. Here we have, this is basically how it works, right? We start with a 2-coordinate system. In other words, where we have a central atom with 2 atoms on the side here. So the VSEPR notation is AX2, right? Means that we have 2 bonding pairs around the central atom. For example, beryllium dichloride. What is the Lewis structure of beryllium dichloride? The Lewis structure of beryllium dichloride is something like that, or you can use lines. These are just different notations. So if you've basically got 2 bonding pairs around the central atom, it's linear. Very simple. Now let's look at what happens if I jump to 3. So let's take the Lewis structure of boron trifluoride. Okay? Now notice number of electron groups. That should say number of electron groups around the central atom. Let's take BF3. BF3, what is the Lewis structure of BF3? We just had it a moment ago. The Lewis structure of BF3 is boron. Boron has 3 valence electrons. Fluorine, which has 7. And basically that can form a bond, those can form a bond, those can form a bond. And so the Lewis structure for boron trifluoride would be something like this. It's an example of, it deviates from the octet. I've just drawn, you can use the 2 dots or the line here, it doesn't matter. Notice that the boron atom has how many, before we look at the table, how many electron pairs around the boron, the central atom? How many? 3. There are 3 electron pairs in total. So, if there are 3 electron pairs, there are the molecular geometry is trigonal. We call it trigonal planar. It's flat as a pancake. Now, let's take an example where we have SO2. If we draw the Lewis structure of sulfur dioxide, let's do that. Sulfur dioxide, SOO. Oxygen has 6 electrons. I'm just putting them in. Sulfur has 6. All right. We need to get, now of course one needs to practice this. I've been doing this for 15 years. That's why I can do it so quickly. So if you can't, don't worry about it. So the Lewis structure of sulfur dioxide would look like this. All right, that's the Lewis structure. Oops, no. Yeah, like that. And it, in fact, can have the expanded octet because it's sulfur. Now, how many, look at the Lewis structure, how many electron pairs are around the central atom? How many? How many? Okay, 5, yes, that's correct. That's a very good point. there are 5 electron pairs around the sulfur atom. How many atoms around the sulfur atom? 2. 2 oxygen atoms. Right, so if we want to actually get the electron group geometry, if we have multiple bonds, we count the atoms plus the lone pair. So in fact what this is, it's in fact got essentially 3, if you want, 3 electron, well it's got two atoms and 1 lone pair. So it belongs to this family of compounds here, which are trigonal planar. So we have this Lewis notation here, SO2, and you see that 1 is occupied by a lone pair. So the electron group geometry is also trigonal planar, but what we've replaced essentially one of these with a lone pair, as you saw in the Lewis structure, so we overall have a band structure. Yes?
I'm sorry, but I don't understand why it's 2. Because don't we have more bondings? Or
Yes, we do. But if you have pi bonds, or if you have double or triple bonds, those count as 1.
Oh.
Those count as 1. That's very important. All right? So don't get confused. The point is that you need to figure out what the total number of electron pairs are around the central atom, counting the lone pairs as well, which will give you the electron group geometry. And then to figure out the molecular geometry, you have to determine which are bonding pairs and which are lone pairs, or how many lone pairs you have, and that will distort the parent geometry. So you can think of this as the parent geometry, and if I start replacing these atoms with lone pairs, it's going to change the molecular shape, isn't it? Because here I've got a lone pair. The molecular shape of that thing is bent, because there's not an atom sitting here, it's a lone pair. But in order to figure that out, you first need to start here with the electron group geometry. Now let's continue. Here we've already looked at this, but I think now you're understanding the bigger picture, I hope. Here I have a situation that's where I started, for example, with methane. I have 4 bonding pairs around the central atom, and all of them are bonding pairs. That's tetrahedral. Ammonia has also got an electron pair geometry that is tetrahedral, but its molecular geometry is trigonal pyramidal because I have replaced one of the bonding pairs with a lone pair. I can also, with water, its electron group or electron pair geometry is also tetrahedral, but I've replaced, in this case, 2 of the bonding pairs with 2 lone pairs. So its geometry is bent. And it's as simple as that. You need to just basically count the number of electrons around the central atom, not taking into consideration pi bonds. So you've got multiple bonds, you just look at the number of atoms, then figure out how many lone pairs there are, add those up, that's going to give you the electron group geometry, all right? And then look at the central atom and see how many lone pairs do I have. And if, for example, if you've got no lone pairs, if it's tetrahedral, it will be tetrahedral. If there's 1 lone pair, it will be trigonal pyramidal, and 2, it will be bent. Yes?
I just have a question about the A.
Yes?
Does it ever change, or?
No, it's just a notation. A is just the central atom. This is just the notation we have. X is the number of bonding pairs, E is the number of lone pairs. It's just a notation. Right, now things get even a little bit more complicated. Here I now have an electron group geometry with 5 electron pairs around the central atom. All right? This is only possible in elements that have the extended octet, because of course 5 electron pairs is 10 electrons. So if I've got 5 electron pairs around the central atom, in other words a total of 10 electrons, those could be bonding or lone pair, it doesn't matter. The electron group geometry is trigonal bipyramidal. We call it trigonal bipyramidal. It comes from the name trigonal, which is flat as a pancake here. That's trigonal, planar. Bipyramidal because there's 2 pyramids. So it's 2 pyramids built from a trigonal planar coordinates in the middle here. Anyway, 5 phosphorus pentachloride would be trigonal bipyramidal. So this molecule has the same electron pair geometry as its molecular geometry. It's the same, because all the electron pairs are bonding pairs. But let's take, for example, sulfur tetrafluoride. If we draw the Lewis structure of sulfur tetrafluoride, let's do that. Sulfur has the potential of an expanded octet because it has access to d orbitals. So let's draw it. SF4. Sulfur is the most electropositive element. It goes in the middle. Fluorine, we have 4 of these. Fluorine has 7 valence electrons. Let's put them in for each fluorine atom. And sulfur has how many? How many valence electrons? 6. It's in the same group as oxygen. 1, 2, 3, 4. What do I do with the remaining 2? Make them a lone pair. That's the Lewis structure of sulfur hexafluoride. Oh, tetrafluoride, sorry. It's got a lone pair. How many electron pairs do I have around the sulfur? How many electron pairs? How many? 5. 4 bonding pairs, there they are, and 1 lone pair. That's an electron pair. So the total number of electron pairs is 5. 5 electron pairs, meaning it's going to belong to this family of molecules here. Number of electron groups 5. Next question. Are all of these 5 electron pairs bonding pairs? Yes or no? No. I have a lone pair. And that lone pair is going to distort the geometry of the actual molecules. We're going to get a different molecular geometry. And if I've got 4 bonding pairs and 1 lone pair, I have a trigonal, a seesaw. We call it seesaw. Right? It looks like a seesaw in a park, right? So the lone pair sits in the equatorial plane, and that's the molecular geometry. What if I have something like ClF3? If I draw the Lewis structure of that, you can do this as a homework exercise, you will see that, in fact, we again have a total of 5 electron pairs around the chlorine atom, which is the central atom in this case. And so the electron group geometry is trigonal bipyramidal, but we end up with 2 lone pairs in this case, and that gives us a T-shaped molecular geometry, and so on. Finally, here at the bottom, it's also possible to have, here we have xenon difluoride. If you draw the Lewis structure there, you'll see that in fact, you end up with a linear molecule. The molecular geometry is linear, in fact, because we have 3 sets of lone pairs around the central atom. So the electron group geometry or electron pair geometry is still trigonal bipyramidal, but because 3 of those groups are lone pairs, we end up with a linear molecule. And finally, if we've got a total of 6 electron pairs around the central atom, we can play the same game. So we can have, in this case, sulfur hexafluoride. How many bonding pairs in sulfur hexafluoride? 6. All of them are bonding pairs. In fact, let's draw the Lewis structure of sulfur hexafluoride, just to check that. I think, let's draw the Lewis structure of sulfur hexafluoride. Sulfur hexafluoride can undergo the expansion of the octet. So I'm just going to prove this to you now. Each fluorine atom has 7 electrons. It's a halogen, group 7. So I'm putting in the electrons. And sulfur has how many valence electrons? 6. It's in group 6. Sulfur is under oxygen in the periodic table. I'm using big circles for those. 1, 2, 3, 4, 5, 6. So there we go. All the fluorines are happy. They all have 8 electrons around them. And the sulfur has 12 electrons around, which is perfectly okay because it has d orbitals, so it can undergo an expansion of the octet. Let's draw this a little bit better. So the dotted line means that, this is another way of drawing it incidentally, to give it some spatial three-dimensional character. Alright, so it's got a total of how many electron pairs around the central sulfur atom? 6 electron pairs. All of them are bonding pairs, right? So the electron group geometry is the same as the molecular geometry, octahedral, octahedral. So its molecular geometry is octahedral, its electron pair geometry is also octahedral. Let's take bromine pentafluoride. Let's draw the Lewis structure of bromine pentafluoride and see what we get. Bromine pentafluoride. Just put them in. How many valence electrons does fluorine have? 7. So just to save time, I'm going to draw the lone pairs like that, which is perfectly okay. Just to save time, you can do it, that's fine. How many valence electrons does bromine have? Where is bromine? What is bromine? It is a halogen, so how many valence electrons? 7. 1, I'm just using a bigger circle, 2, 3, 4, 5, and what do I do with the remaining 2? Lone pair, yes. So that's sort of like, that's me scribbling around. Let's draw a neat Lewis structure. It would be bromine. Oh, actually, let's just draw it without spatial consideration for the moment. That is the lone pair. Oh, sorry, I'm missing one. There we go. All right, that's the Lewis structure. Okay, I'm not drawing. You should try and draw a Lewis structure. Actually, if you are taking the spatial orientation into consideration, right? But before you can get there, you first need to figure out what the geometry is. So, how many bonding pairs do I have in this molecule? How many? Listen carefully to the question. How many bonding pairs in this molecule? 5. How many lone pairs in this molecule? 1. So how many electron pairs? 6. So I have 6 electron pairs, meaning that what is its electron pair geometry? Octahedral. What is its molecular geometry, however? Square pyramidal. So in the square pyramidal permutation, if I can call it that, one of these bonding pairs becomes a lone pair, and that's exactly what I have here. I've got five bonding pairs and one lone pair, and what you would end up with is a molecular geometry that is square pyramidal. You'll follow this. It's a pattern. You basically write the Lewis structure, count the number of electrons, figure out, first of all, what is the electron pair geometry by summing the number of bonding pairs and lone pairs, except if you have double bonds where you just, or triple bonds where those counts as 1. That gives you the electron group geometry, and then you look at how many lone pairs you have to figure out what the molecular geometry would be. And it's as simple as that. But do you appreciate that if you can't draw a Lewis structure, you can't figure out the molecular geometry? That is the point. So now I've tried to condense down the most important things. The last possibility is something like this, where we have a square planar geometry. Here we have, for example, xenon tetrafluoride. Perhaps you can do this as a homework exercise. If you draw the Lewis structure, you'll end up with something that looks like that, and that would be square planar. 2 lone pairs, 4 bonding pairs, so a total of 6 electron pairs. The electron group geometry is octahedral, the molecular geometry is square planar. And you can also go to 7, by the way, but you also have an electron group geometry of 7. For example, IF7, but we're not going to go there in this course. So what I expect you to really know and be able to predict from the Lewis structure is figuring out from the Lewis structure what the electron pair geometry is, and then predicting the molecular geometry, and then actually drawing it in three-dimensional space, right? Okay, more about this in the PBL session, because we've got a whole PBL devoted to this. Now, the very last, okay, well, examples, let's practice. We've already done so. The last thing I want to discuss today, and I'm not going to go into too many details here, I just want, something I mentioned earlier on, please just appreciate that bonds between atoms, atoms have different electronegativities, right? Something we will be discussing today, hopefully in the pre-discussion of the PBL. And these different electronegativities result in either a bond being non-polar, if there's no difference between the electronegativity, or polar covalent, or if the electronegativity is so big, it can even be ionic, right? So what we see, for example, here is ammonia, and nitrogen and hydrogen have different electronegativities, obviously. And you can see here, if we actually model this on a computer, you can see that these bonds, these nitrogen-hydrogen bonds, are in fact polar, right? Because they've got a difference in electronegativity. Overall, each individual nitrogen-hydrogen bond is polar, but the molecule as a whole is also polar. And here we have some more extreme examples. Here we have, for example, lithium hydride. You see so this is the difference here. We have a negative extreme and a positive extreme, so electronegative, electropositive. So here you see these extremes here. So these are highly polar bonds, in fact, ionic bonds. Look at hydrogen. There's no difference in the electronegativity here, so we have everything's colored the same. I just want you to appreciate that we have a difference in the polarity, or the difference in the electronegativity between atoms, which affects whether a bond will be polar or not, and whether or not a molecule will be polar or not. So that's basically what I really want to end off with today. We do have a table of electronegativity, which is given on a relative scale.